Okay, so the first thing that I have on here is chapter 5, and I took your guys' input and suggestions, and I just went for sections 4 and 5. Seemed like what most people wanted to see. So the first section we're going to do is section 4, complex zeros and the fundamental theorem of algebra. So the main type of problem that we've done from here is just finding all of the zeros of some polynomial when we have real and complex zeros. So that's what I'm going to do. This problem has 4 steps. So it's a multi-step problem. We've done a few like this before, but it doesn't hurt to get a refresher, and it seemed like people wanted to go over this. So I did throw a theorem in there that's in this section that I think is helpful to be reminded of, and it's the conjugate pairs theorem. So this is really important, and it comes up in a lot of the questions that we talk about. So as a reminder, I put that in here, and that just says that if a plus bi is a 0, its conjugate is also a 0, which is just a minus bi. So that comes up a lot where they'll give you a 0 of a polynomial and then ask you what the other ones are. And it's helpful to know that when you have complex zeros, they come in pairs. And if something's a 0, its conjugate is also a 0. So I just threw that in here as a reminder, just so we could all refresh our memories of that. But first, I'm going to start with this example, which is find all zeros of the following polynomial function. So we have f of x is equal to x cubed minus 4x squared plus 4x minus 16. So a good first step to do is ask yourself how many zeros you actually need to find. And we've talked about the fact that the degree of f of x is the number of zeros. So I'll write that down. But we know that the degree of f of x is equal to the number of zeros. And these are complex, real, it's all the zeros. So if you know the degree, you know how many zeros you need to find. So first of all, I have a Zoom poll, and it's going to ask you how many zeros there are. So I will launch it, and you guys can tell me how many zeros we need to find. And it is anonymous. All right, just a few more seconds. There's just a few people that haven't answered. Okay, so I'm going to end it. So, all right, we had 81% of you say that there's 3 zeros, and then 19% of you said that there's 6. So I know why it was split that way, but the correct answer is 3. And does anyone want to share why they said it was 3?
Isn't it all based on the coefficient of the leading term?
Yeah, I think you meant the exponent, but yes.
Yeah, that's what I meant.
So the exponent on the leading term is the degree. I know that some of you put 6, and I think the misconception there comes in because you added up the exponents here. But just a reminder that when we're given a polynomial in this form, we don't need to add exponents. It's just the exponent on the leading term. So the correct answer is 3 here. So we have 3 zeros to find. Okay, so that is kind of like step 1. I don't know if it's even really a step, but just figure out how many zeros you have to find. Our next step is to apply the rational root theorem that we know that tells you the possible rational roots you have. And this is where we find like that long list of possible ones, and then we try plugging some in and just hope that we get lucky and find a good one early on. So let's go ahead and do that. So we're going to apply our rational roots theorem. And this is when we have those 2 elements, p and q, and their factors, and then we make our list of all the possible roots. So first, we need to identify what p is, and p is all of the possible factors of 16. So I'm going to list those out. So first of all, I know that I have 1 and 16, but I've got 1, 16. 1 times 16 is 16. And then I have 2 and 8. And then I also have 4 times 4. So those are all of my possible factors of 16. And then my next step is to do the same thing, which will be Q, and that is your factors of 1. And that's because 1 is the coefficient on x cubed. But that makes it really nice because the factors of 1 are just 1. So that's nice and easy. So once you do that, then you have to figure out what P over Q is. And those are all of your possible rational roots. So that means that I take each element from P and I put it over each element in Q. So it makes it easy though, because Q is only one thing and Q is just 1. So we just take each element from P and put it over 1. So it ends up being just 1, 16, 2, 8, and 4. So once we have our possible rational roots, which are these ones right here, our next step is always to test a few out and see if they work. So to test a few out, we take, you can pick one. So you just pick one from this list and you're going to plug it into your function and you're hoping to get 0 out. And to remind you of why that is, it's because we have the theorem that says if we plug in a number and we get out 0, then that happens to be a root. So we have that whole long theorem of, it's a little bit of like the remainder theorem, and if you get a remainder of 0, then it's a root. But to make it simple, we're just going to plug in a few of our possible roots and hope to get 0, because that means that that number is a root. So to test a few of these out, I tend to just start with 1. I don't know if that's just me, but that one's usually easiest. So f of 1 is going to be 1 minus 4 plus 4 minus 16. Okay, well, sadly, that does not give me 0, so that one doesn't work. So next, I guess I just gravitate and go in order, so I'll go with 2. If I plug 2 in here, I get 8 minus 16 plus 8 minus 16. Sadly, this does not give me 0 either. And just to not sit here and waste any more of our time, 4 actually does work, so I'm going to plug 4 in. This would have been my next guess, but sometimes it's really tedious to sit here and plug a bunch of these numbers in. So this gives me 64. Let me go back up so you can see the function. 64 minus 64 plus 16 minus 16, which is 0, and we're really happy because now we don't have to keep doing this. So that means that we found one of our zeros, and this one is 4. So woo, we found one of the 3, and now we have to find 2 more. So let me just write down what this gives us. So we know that 4 is a 0 of f of x. And when we get a 0, we know that there's also a factor of f of x associated. So we know that x minus 4, because we have x minus that 0, is a factor of f of x. So in other words, I guess that means that f of x can be written as x minus 4 times some other piece here. And that's the piece now that we want to find. So we've already found that f of x can be written as x minus 4 times something else, but now we want to find this because this piece is going to give us our remaining zeros. So we want to find this. And if you remember, we do this using either synthetic division or polynomial division. Either one works. I tend to prefer synthetic division, and I think most of you do from past experience. So I'll just go ahead and do synthetic division, but you can do polynomial division as well. So to find this piece, we're going to take f of x and divide it by x minus 4. But I'm going to use synthetic division to do that. So I'm dividing by x minus 4. So for synthetic division, that means that I put a 4 up here. And then I list out the coefficients on each term in my polynomial. So that means I have 1, -4, 4, and 16. All right, so your first step in synthetic division is to bring this number down. So this just is 1. And then we do 4 times 1, which is 4. -4 plus 4 gives me 0. And then 0 times 4 is 0. 4 plus 0 is 4. And then, oh, I'm sorry, guys, this should be a -16. I was like, that's not going to work. That should be -16 up top. But 4 times 4 gives you 16, and that gives us a remainder of 0, which is what we wanted. So I know I say this like every time, but if you're dividing by a factor, you should always get 0 as a remainder. So if you don't get 0 here, something's off. Need to go back and check your work. Maybe you just did the division wrong, or maybe it actually wasn't a 0, what the number that you found. So if you don't get a remainder of 0 when you do synthetic division or polynomial division, you have a problem here. So good, we got 0, which is what we wanted. And then we remember that these numbers right here give us our coefficients on our new polynomial. So we have x squared plus 0x plus 4, but that's just equal to x squared plus 4. So now we found that like other missing piece. So to put this together, we know that f of x is equal to x minus 4 times x squared plus 4. I'm going to stop here. Does anyone have any questions? You can always interrupt me. Like, you don't have to wait for me to ask, but I'm just going to give the opportunity if there's any questions at this point. Okay. So now that we have that other piece, all we have to do is find the zeros that are associated with that piece here. So we want to know where x squared plus 4 is equal to 0. And this one's nice. Usually we get something that we have to do the quadratic formula on, but this one's kind of nice because you just get x squared equals -4. And that gives you x is equal to the positive and negative root of -4, which is just 2i and -2i. So you can see, as I mentioned above, the conjugate pairs theorem tells you, that if you have a complex 0, its conjugate is also a 0. So you can see that that's true here because we have 2i as a 0 and then also -2i as a 0. Anyways, that gives us all of our zeros. So we have, what do we have? 4, 2i, and -2i. Sorry, that's a terrible I. And that is our final answer. Are there any questions on anything that I did before I move on to the next problem that I've got?
So for problems like these, do we only plug in like the PQs until we get one that works and then we do synthetic division from there? Or do we just is that how it should usually go with most problems like these?
Most of the ones that we've done in class are the ones that you guys have been given. You're usually given something like a polynomial that has 3 zeros, something to the 3rd degree, which if we've got something like that, as soon as we find 1 0, we're able to factor it down into a quadratic times something. And you know how to solve a quadratic. That's why we usually only find 1 0. If it's a 3rd degree, because you know that the other piece is a quadratic, you guys can use a quadratic formula. That's like really easy to do. If it's a higher degree, sometimes sometimes you can factor what's left over. It's kind of different, but I think the only ones that we've really done are third degree ones because those ones are kind of the most simple example. So that is why we only find one, is because then our other piece is a quadratic.
Okay, so then usually if it's third degree, just like keeping an eye out to make sure that it's third degree when we're solving it then.
Yeah.
Okay, thank you.
If it's third degree, you should only need to find one because then you can do a quadratic as your other piece and you guys know how to solve that. I think there's some examples in the book, but I think there was only like one or two where it's like a fourth degree or a fifth degree or something, just because they take a little more time. But I don't think you've ever had to do anything higher than that, like on an exam.
Yeah, thank you.
Yeah, no problem. Anyone else? All right. So that's all I did for section 4, because that kind of combines everything that you talk about. So the next section that I have listed on here is properties of rational functions. And I just wrote down a few definitions or concepts just to remind you of them. So I wrote down things about vertical asymptotes, horizontal or oblique asymptotes, and just like the definition, kind of how to find them and stuff. So those are the 3 concepts I'm going to focus on from section 5. So to refresh our memories, the vertical asymptotes. So the rational function in lowest terms has a vertical asymptote x equals r if r is a real 0 of the denominator. So what does that mean? That means if our rational function is in lowest terms, our zeros of the denominator are going to give us the vertical asymptotes. And then next we have the horizontal or oblique asymptotes. So this is where in the definition they kind of write out the general form of a rational function. So instead of just saying p of x over q of x where they're polynomials, you can actually visualize it now because it's written out as a polynomial over a polynomial. And this helps you later on with one of the cases. But with horizontal or oblique asymptotes, we're really concerned with the degree of the numerator versus the degree of the denominator. So for the definition's sake, the degree of the numerator is defined as n, and the degree of the denominator is m. So this is where you've got a few different cases that you have to go through and ask yourself which one is true for whatever rational function you're given. So if, sorry, didn't mean to scroll. If the degree of the numerator is less than the degree of the denominator, then the line y equals 0 is a horizontal asymptote. If the degree of the numerator equals the degree of the denominator, this is where we read off those leading coefficients on our first term, and that line is a horizontal asymptote. If the degree of the numerator is 1 more, then we have an oblique asymptote, which you have to find using polynomial division. And then if the degree of the numerator is 2 or more greater than the degree of the denominator, then there are just no horizontal or oblique asymptotes. So that one's my favorite case. But I put a few examples down here, so I think we're going to do 2 and go through the process of finding the vertical, horizontal, or oblique asymptotes, if there are any, of each function. So first of all, I have another poll for this, so let me launch that. Okay, so this is just a true or false. So it's to find the vertical asymptotes, it needs to be in lowest terms. So I'm going to launch that, and it's anonymous. You guys can just put your answer in when you get a chance. All right, I'm just waiting on a few more people. Okay, so most of you said true, 80%. You said false, and then I'm not sure. So those of you who said true, you are right. It is true on this, and I did state that up here that it needs to be in lowest terms. The reason why is that if you don't put it in lowest terms first, and you just go straight in to finding zeros of the denominator, you might accidentally mislabel something that might be a hole in the graph, and you might say that that's a vertical asymptote. So it's really important that we put things in lowest terms, because when we go through that process, we find holes in the graph. And if you don't do that, then you're probably going to accidentally mislabel something. So good. It does need to be in lowest terms. So what I'm going to do is walk through the steps on this first problem, h of x. And then once we do that together, I'm going to have you guys do 2 on your own and try that out. So let's start by doing number 1 together, and then I'll give you a chance to go for it on your own. So the first thing that I'm going to do is find my vertical asymptotes. So like I just said, it needs to be in lowest terms. So let's go ahead and factor this thing down and see if it's already in lowest terms or if there's anything that we can cancel out. So first I'm going to start by factoring my numerator, which is x squared plus 6x plus 5. And I always write it out. I always do the little x, but you guys can do whatever method that you want. So I know that this factors into x plus 5 times x plus 1. And the next thing I need to do is factor the denominator, which is 2x squared plus 7x plus 5. Using my little x method again, my favorite thing, the thing I was taught and I've never left behind. So remember that when you're factoring something that doesn't have the coefficient of 1 on the x squared term, you can't just go straight to saying like, oh, this is x plus 5 times x plus 2, because that's not going to give you the right answer. So remember that if you have something other than a 1 here, there's kind of like an added step in here. So this is equal to 2x squared plus 2x plus 5x plus 5. And you have to do that like little added step of factoring by grouping. So you have like these two together. I'm not going to go too in depth here because this was from a while back, but if you do have any questions on factoring or just need more practice, feel free to like reach out to me or come to office hours. I'd totally go through it with you there. I just don't want to take too much time here doing it. So long story short, this factors down into 2x plus 5 times x plus 1. And then we see that we do have some stuff that cancels out. So h of x is equal to x plus 5 times x plus 1 over 2x plus 5 times x plus 1. Okay, so really nice because we have a common factor in the numerator and denominator, and that means that this cancels out. So that gives you that there's actually a hole at -1. I'm not going to go too in depth on that part, but I just want to throw that out there and say that that's why it's really important that your rational functions in lowest terms, because if I didn't cancel these things out, I would say, oh, there's a vertical asymptote at -1. And that's not true because -1 is actually a hole, which means our graph isn't defined there. So just to reiterate, make sure you put it in lowest terms before finding your vertical asymptote. So now we know that we need to just find the zeros of the denominator, since that's the definition of a vertical asymptote. So we just need to know where 2x plus 5 is equal to 0. Does anyone want to take a shot at what this is?
-5/2.
Yep, awesome. All right, so we found our vertical asymptote, and then next we just need to find the horizontal asymptote. So we have that, and so this is where we want to compare the degree of the numerator and the degree of the denominator. So we've got a few cases here. The degree is going to be the degree of the numerator is going to be less than the degree of the denominator. They're going to be equal, or the degree of the numerator is going to be greater than. Does anyone want to take a shot at which one it is? So Are they equal? Is the numerator less than, or is the numerator greater than?
They're equal to?
Yeah, good. They're equal. Both of them have a degree up here too, but even when you put it in lowest terms, their degrees are equal still. So if they are equal, we just have to read off the leading coefficient on in the numerator and in the denominator. So technically we've got like a 1 here. So if we just read that off, we get 1/2. So that means that we have a horizontal asymptote at y equals 1/2. Are there any questions on this process before I let you guys attempt the next one on your own? Okay, cool. So this next one is p of x is equal to 4x squared over x cubed minus 1. So just go ahead and find vertical, horizontal, and oblique asymptotes, if any. So I'm just going to let you guys go for it on your own. And then when you finish, send me a private chat of your answers. So you send it privately, that way not everyone's seeing it. So when you finish, send that to me. That way I know where you're at, and then we'll talk about it briefly.
Could you possibly scroll up so we could see like all of the horizontal and oblique stuff? Thank
Yeah.
you.
Here, I can like zoom in a little too. So if you want and you find the vertical asymptote, you can go ahead and send that, and then send the horizontal or oblique ones after, whatever. Just send a private chat when you've got some of your answers. I'm not checking to see if it's like correct or anything. I just want to make sure everyone's going through and doing it. Okay, good. I'm getting some answers in. Good. Good. These look really good. Most everyone got both of them right, actually. But you can keep working on it. I'll just briefly kind of explain what they are. That way you can check your answers and check your work. So it's good to note that P of X is already in lowest terms, so there's actually no work to do before we start looking at the vertical asymptotes and the horizontal asymptotes, which is really nice. So P of X is in lowest terms. So to do the vertical asymptotes, we just want to know where the denominator is equal to 0. So we set x cubed minus 1 equal to 0, and we get x equals 1. So if you got a vertical asymptote of x equals 1, good job. And then to do the horizontal asymptote, we just want to compare the degrees of the numerator and the denominator. So the degree of the numerator is 2, and the degree of the denominator is 3. So the degree of the numerator is less than the degree of the denominator. And as a lot of you noted, that means that we have a horizontal asymptote at y equals 0. And I'm just going to go up and clarify that it does say if the degree of the numerator is just 1 more than the Oh, sorry, hold on. Never mind. Ignore me. We're good. I was getting confused with the last two cases. Anyways, so now we have our horizontal asymptote at y equals 0, and we're good. So if you got those two, then you got both of them correct, and most of you actually did, which is great. Okay, so that is all I have for chapter 5. That's just a few things from 2 sections, but hopefully that's a little refresher. And then the next thing that we're going to look at is some stuff from chapter 6, which is logs and exponentials. So I think most people wanted some help with the last few sections in chapter 6, so where you get into like properties of logs. So I did section 5, which is those properties, and then after that I've got some stuff from section 6, which is logarithmic and exponential equations. So it's a little more like solving in section 6. So first of all, I put at the top of the page some of the properties. This I just took straight from the book. So you'll probably find this in your notes or in the book or something. So I put that on here as a quick refresher of everything that we know. And then I have, I think, 4 true or false questions. And these true or false questions are just using those properties that are listed above. So each true or false gives you like a logarithmic or exponential kind of expression that they've kind of attempted to use the properties to simplify it or expand or something. So your job is to look and use the properties and see if they did it right. So I will go through 1 and 2 with you guys. They're not too long. And then I'll let you guys kind of attempt 3 and 4 on your own a little bit. So number 1 is true or false. Ln of x plus 3 minus ln of 2x is equal to ln of x plus 3 over ln of 2x. So let me find the exact rule up here. So I think it's this one. Circle that. So this rule says that if we have 2 logs with the same base and they're being subtracted, it's the same as combining them and just dividing what the log was being taken of. So it's important to note that we have ln, which is just log base e. So these do have the same base. So we have ln of x plus 3 minus ln of 2x. And using this property that I circled up here, we can go ahead and combine these into 1 using division. So this should be equal to ln of x plus 3 over 2x. So you can see that this is actually not equal to what the problem says. So the problem has ln of x plus 3 over ln of 2x. And those are not the same thing. So this one is false. Does anyone have any questions on why this one's false? Okay, so for number 2, we're given log base 2 of 3x to the 4th is equal to 4 times log base 2 of 3x. So it looks like what they've done is tried to take the exponent here and bring it out to the front. That's all that's changed here. But we want to see, was that a valid move? Like, was that okay to do? So let's go up and use our properties here. And it is, which one is it? Oh, this one right here that I just circled, where you've got log base a of m to the r is equal to r times log base a of m. So the issue here is that we have log base 2 of 3x to the 4th. The only thing that's raised to the 4th power here is the x. The 3 is not actually raised to the 4th power. We would be able to pull this exponent out if we had log base 2 of 3x to the 4th. If the whole entire thing in the parentheses was raised to the 4th power, then we would be able to move that out. So this is equivalent to 4 times log base 2 of 3x. But the issue is that in the problem that we're given, the exponent of 4 is only on the x. It's not actually on the 3. So this one's false as well. Does anyone have any questions on why that one's false? Okay, so I want you guys to attempt 3 and 4 on your own. So 3, I have a Zoom poll for, so I'm gonna let you guys work it out and then say if you think it's true or false, and we'll talk about that one, and then we'll do 4 as well. I don't think we're gonna get to, well, we're not gonna get to section 6, but that's okay because I am flexible, so we can do this on Wednesday, or you guys can attempt it on your own and just ask me questions, but this is some extra practice that it seemed like everyone wanted, so that's okay if we're not getting to section 6. I just wanted to make extra problems since you guys asked for them. So we'll just try and focus on this section, and then we can revisit the worksheet on Wednesday if you guys want to. So I am going to scroll up so you can see all the properties. Try and do number 3 and decide if it's true or false. And I'm going to launch a poll and you guys can vote once you have an answer.
Quick question, where can we find this sheet again that we're doing?
It's just on today's recitation activity. So on the 30th, the 11:30 recitation activity.
Okay, I wasn't able to find the recitation activity.
I know why, Sophia.
Okay.
It's because it's an undated assignment. I
Okay.
had trouble too.
Okay.
But yeah.
Where do I go to like modules or something, or?
It's just under assignments. There should be a section that says like undated,
Okay.
and it's like at the bottom of that one.
Perfect. Thank
It's
you.
hidden. Yeah.
Yeah, sorry, I didn't assign a due date because there's nothing to be turned in, and I didn't want to make it seem like you guys had to turn this stuff in. So yes, it is an undated worksheet, but it is on there. But Taylor's right. It's just under like the undated ones. Okay, so I have like half of you have voted, so I'm gonna give it a little more time. Just gonna give it like a minute or so. Okay, so I'll leave it open. You can still submit your answer, but let's start talking about it since we only have a few minutes left. So there is a property up here. It is, make sure I circle the right one. Yeah, it's this one right here that says that a to the r is equal to e to the r ln of a. So we can use this on what we're given. So 2 to the x, just using this property, should be equal to e to the x ln of 2, which is exactly what this is. So this one checks out as true. That was like a terrible true, which most of you guys said. So that's good. About like 75% of you said it was true. Okay, so we've got about 3 minutes left. So I want you guys to just attempt number 4. So just attempt this one, see if it's true or false. And when you finish, send me a private chat just saying true or false, depending on what you get. And I'll scroll up in case you need the properties. Good, I'm getting some answers in. They all look really good so far. Good. So since we only have a minute left, I'll just go ahead and spoil it. It is false, which actually everyone that chatted said it was false. So that's great. So this one is false. If you guys have any questions on why it's false, we can discuss it Wednesday, or you can like hang around and ask me, or office hours too. I'm going to stop here for today. We can keep working on the log review in here on Wednesday, or we can just do Q&A, whatever. Like I said, I'm really open. Like that's your time on Wednesday, and we can use it to review whatever content that you guys want. As a reminder, I have office hours tomorrow and Thursday, and those are the last ones. I'm thinking about holding a study session for your final, so I will let you guys know Wednesday, or like send out an announcement or something. So I think that's all I have to say. This worksheet isn't being collected. You don't have to finish it. Like we're done turning in assignments. And then within the next few days, I'll try to finish grading your last 2 ones. That way you have an idea of what your recitation grade is. And then do your FCQs. I think that's everything that I have to say. But are there any questions? Okay, sweet. I'm getting some thumbs up. So you guys are free to go. Have a great day, and I will see you Wednesday.